Let's continue talking about molecular shapes and finish off section 2 with a few more details. First of all, let's talk about a little bit of geometry fine-tuning. So different types of electron domains exert different amounts of repulsion. And of course, if you have more repulsion, then you need more space for that type of electron domain. So when I'm talking about different types of electron domain, what I mean are you could have a single electron in the rare case of having an odd number of valence electrons, or a single bond, or a double bond, or a triple bond, and lastly a lone pair. Lone pairs occupy the most space because they're not focused towards another atom. They're in very diffuse orbitals that push sideways quite a bit. The implication of this, for example, is that if we look at these structures in a perfectly tetrahedral structure like methane, we do get an exact bond angle of 109.5. But in ammonia, where we have this non-bonding region, this region exerts more pressure against those bonds and pushes them very slightly closer to each other so that we get a bond angle experimentally of 107 degrees. And in water, again, the presence of two non-bonding pairs exerts even more pressure and squeezes that bond angle down to an experimental value of 104.5. Now, the point of this is not that you should be able to predict the resulting bond angles. If I ask you for bond angles, it's always good to just give me the approximate value of 109 degrees. But understand that more repulsion is going to squeeze those angles closer. And the main idea is that we need more room whenever possible for non-bonding pairs, and that's going to determine some of the shapes that we talk about next. Similarly, double bonds take up more room than single bonds because they exert more repulsion because there's more electrons there. So if we look at a molecule like this, CCl2O, the double bond exerts more pressure because there's more electrons here, so it squeezes this bond angle to being smaller than 120 degrees, whereas this is slightly larger than 120 degrees. Sometimes these sorts of details matter in the properties of the molecules, but you do have to be careful about applying them, because if you apply them too blindly, you'll lead to incorrect conclusions. So for example, if you apply this idea to a molecule or an ion that looks similar with one double bond and two single bonds, you might very well think that this is a bigger angle than 120 and this is a smaller angle than 120. But that's wrong, because the nitrate, as we've seen, is best viewed as the average of three equivalent resonance structures. So in fact, all of the bond angles in the nitrate molecule are exactly 120 degrees, because all three bonds are technically equivalent. So we have to be careful. Nonetheless, this will give us insight into trigonal bipyramidal based structures. So it turns out in trigonal bipyramidal electronic geometries, there's two non-equivalent positions. These two bonds that I'm pointing to now are axial bonds. Think of this as being sort of the axis of a globe, and if you rotate the globe about its axis, the resulting positions, these three positions, the remaining positions rather, are equatorial. They would all be on the equator of the globe that's rotating about its axis. These positions we say are inequivalent or non-equivalent in the sense that if you rotate this molecule, there's no way that you can put this atom in a position where it's pointing up and down and that you have an atom that is up and an atom below. You can't make this replace the axial position by any sort of rotation. They're fundamentally different positions, and they lead to the important molecular geometries associated with trigonal bipyramidal structures. So for example, this is a very important principle. Lone pairs, non-bonding pairs, because they occupy more space, will always occupy the equatorial positions in a trigonal bipyramidal structure, because there's fewer bonds to interact with and cause repulsion. There's only 2 bonds at 90 degrees away, and that leads to the characteristic structure of the resulting molecule. So if we look at our table of structures built on 5 electron domains, if there's no non-bonding pairs, then we end up with a trigonal bipyramidal molecular geometry like PCl5. If there's one non-bonding region, since it always occupies an equatorial position and never an axial, the resulting geometry we describe as seesaw. I'll help explain that a little bit, but if you can see these 2 positions as the leg of a playground teeter-totter or seesaw, and these as the boards that you would sit on, you'll see that structure. I'll show you later. If there's 2 non-bonding regions, then since they always occupy equatorial positions, the resulting description is that it is T-shaped. Notice this is T-shaped and not T-shaped with a lowercase t, and that's simply because the molecule itself looks like a T. That's the whole point. We're describing the shape. This is not an abbreviation for anything. It's literally the shape of the molecule. Finally, if we have 3 non-bonding regions, since they always occupy equatorial sites, the resulting shape of the molecule is linear. Now let me go back to the seesaw shape and just show you a picture that sort of is more descriptive of the shape. Here's a molecule of SF4, for example. We say it's T-shaped for the obvious similarity between this molecule and a seesaw playground toy. Now, when we go to octahedral shapes, all of the positions are equivalent. There is no equatorial axial because this molecule can be rotated in such a way that any position can be made like another. So for that reason, there's no preferential position for a non-bonding pair to take. So when we describe the shapes, there's no non-bonding pairs, it's octahedral. With one pair, we have a square base and an apex, so that's square pyramidal. If we have 2 non-bonding pairs, then they want to be as far away from each other as possible because of the repulsion, so they will always occupy opposite positions, leaving us with a square planar molecule. Now, in those instances with molecules containing more than one central atom, then we describe the geometry by simply describing the geometry around each central atom separately. So for example, if we look at acetic acid, here's our Lewis structure for acetic acid. Think about each of those central atoms separately, and I'm going to build a table. I think the book does this. Around the first central atom, we have 4 electron domain regions. The electron domain region is tetrahedral. The actual shape is also tetrahedral with bond angles of approximately 109.5 degrees. The second carbon has 3 domain regions, 1, 2, 3, hence trigonal planar. And then finally, this oxygen has 4 domain regions, 2 bonds, 2 non-bonding pair regions. So it's tetrahedral in electron domain geometry. Its molecular geometry around that oxygen would be bent with a bond angle of approximately 109 degrees. Lastly, special case for oxyacids, acids that are built up from oxyanions. In general, the rule is that in oxyacids, the acidic hydrogens are always bonded to the oxygen atoms and not to the central atom. So this is a guideline for building the Lewis structure in the first place. So for this first structure, we might have H bonded to an oxygen, bonded to a chlorine. This will be double bonded to an oxygen with 2 pairs of non-bonding electrons, single bonded to an oxygen with 3 pairs of non-bonding electrons. And then finally, I need 1 more pair on the chlorine. So the geometry around the chlorine would be tetrahedral electronic geometry, trigonal pyramidal for the molecular geometry. For sulfuric acid, I showed an example of this earlier when we were talking about exceptions to the octet rule. The best single structure for this, hydrogens again bonded to the oxygens. Sulfur has a double bonded oxygen. Those are supposed to be two pairs of dots. It's a little bit hard to draw that on my pad here. And then another oxygen and a hydrogen bonded to that. So again, the point I'm making is that the hydrogens are always bonded to oxygens and not to the central atom.